Alright, so some bits on parametric and polar curves, calculation examples for Engineering Mathematics 1. So we have the examples we missed on Wednesday. I was a bit tired, but actually these are fairly complex ones, but they do demonstrate a few good principles you need to remember when you're working with polar curves. So area inside and what's the length of the line of toes. And then we're going to have a look at about surfaces and a few hand waving examples. And for toes hand waving, we're going to need a few extra concepts. So we're going to have a look at the tangents and normals of parametric curves. Copolarization is just a different kind of parametrization if you think about it. Anyway, area inside R equals this circle with the radius, with diameter of square root of 2, and this lemniscate. Lemniscate is a bow tie looking thing, but now it's a lemniscate we're using a sine, so it's a bit slanted. First we solve the intersections. Technical trivial one is the origin, but remember, different curves can go to the origin at different angles, so you need to check all of those. And I originally tried on Wednesday morning multiplying by r. No. Because r equals square root of 2 sine theta there on the circle. Then multiplying by r means multiplying by square root of 2 sine theta. So we need to take the square of that. And now we have the square root of square root of 2 is 2 sine squared theta. That's r squared equals sine 2 theta. We can also write sine 2 theta as 2 sine theta cosine theta. So we have now 2 sine theta equals 2 sine theta cosine theta. Let's get rid of the 2 sine theta on both sides, so we get the result that the intersection is the point where sine theta is cosine theta. And that's true at, well, within the first area. Remember, this will loop around, possibly at 0 points. It's true at theta equals pi over 4. This is also what we got plotting on the classroom. So what we're looking at, we want to know what's the area between these curves. So do I have a pen? Yeah. So we want this area over here. The limit is the circle curve until this angle, which is a pi over 4 until here, and then the limit is it continues from the lemniscate. So this curve which continues until this angle here, which is pi over 2. If you insist, that's 90 degrees, as it says here, and this would be 45 degrees. So integration limits. It's not completely that the one of these curves is on the below and one is on top, because now the intersections are at different angles for each, or that is a different parameter location for each curve, so we need to consider where the parameter is. Let's plot at those ranges and see if we can get the same shape. Yes, we do. So now the red one is the circle segment from 0 to pi over 4. So we need to calculate this area from the circle. So what is area delimited by that circle segment? And then this area, we need to calculate what's delimited by the lemniscate segment. And the dashed line is just pointing at 45 degrees. Area integral is still like that. I'm having a typo here, apparently. Anyway, area integral looks like that. So this is the lemniscate one, so this should be pi over 4. This should be pi over 2. And remember, we're talking about integrals now. This is regular, so this is that's the R for the circle. So okay, and now this is not the bottom and top, just added areas. So that segment plus this segment, and this here, yes, because we had defined the lemniscate as r squared equals sine 2 theta, then we don't need to anymore take the square because it's already here on the r square. Okay, this becomes again 2 sine squared theta. Just a conversion formula, so that part becomes 1 minus cosine 2 theta. You may notice that there's no 1/2 here, so that went in. And so we get 1/2 integral minus cosine 2 theta over 2. And this is already integrated, so remember antiderivative, so the derivative of sine is cosine, the derivative of cosine is minus sine, so the sine is the antiderivative minus cosine, so that's where the minus comes here. And 1 over 4, this so we had the half, and then we get the additional 2 from here, or additional half from here, so half times half is 1/4, and substitutions. And then similarly we're just something funny, because some of those limits don't make sense. Yeah, okay, those limits are wrong. I've done copy pasting, so this should be a 0 and pi over 4. Then it starts making sense. And pi over 8. We're gonna escape somewhere. Then 1 over 4 comes as the cosine equaling 1. And then we got this. Oh yeah, the pi over 8 comes from this one integral of 1/2. So we have 1/2 here, and we substitute it, integrate it. It's 1/2 theta. 0 is 0, and then 1/4 times half is just pi over 8. So that comes from there. And then we get this part, and over from here we got just so one of those goes to 0, cosine 1 pi over 4 to be exact, so that's cosine pi over 2 is 0, but then we get 2 cosine 2 times pi over 2, which is cosine pi. It goes to so cosine pi is minus 1. Minus 1 times minus 1/4 is plus 1/4. So this comes from there. And then we had this integral of this cosine part, well half cosine, so it goes to minus 1/4 sine 2 theta. Correct those, and we get minus 1/4. So 0 sine is 0, and sine 2 times pi over 4 is sine pi over 2, which is 1. 1 times minus 1 over 4 is 1 over 4. So we get here we get this minus 1 over 4. These cancel each other, and all we have left is pi over 8 from this half part. Okay, that was slightly confusing. But just need to be careful. And this is more or less directly from the book. full disclosure, so I would probably myself have divided this integral into two parts and then done each integral at a time to make it less confusing. Then just a reminder, then you need to add all the components together again. Okay, length of the cardioid. So now, usually we would go from 0 to 2 pi, but because it's symmetric, we can take it twice and go only from 0 to pi. And ds is the arc length element, which we in polar coordinate define as change in radius squared plus so this radius part comes from radius squared comes from the other direction. So what's the function distance there, and it scales the sideways distance and then the change in function distance, and we take the Pythagorean element there. We have this r already here, and then this dr over d theta is just the derivative of that. So we could do d theta of 1 plus cosine theta. A we can get on the front, so it's just a constant multiplier there. It doesn't affect the end result other than being constant multiplier. Okay, and d theta of 1 is this goes to 0, and this is the derivative of cosine is minus sine theta. So we grab the a here, and we get minus a times sine theta. Let's plug it in on the formula. So under square root, minus a sine theta squared, well, okay, plus a squared, so this twice, so when we have r twice, so we get a1 plus cosine theta twice, so that is a twice, and so individually it goes like that. Over here, minus a times minus a is a squared, and then we get sine squared theta, and this part is just there, so we do now notice that we have a common term here, and then this 1 plus cosine theta part is 1 plus 2 cosine theta plus cosine squared theta. Okay, so under the square root, this entire thing would be there under square root, so a squared sine squared, this is the constant common term, and then we do have sine squared theta cosine squared theta, which is 1. So what we get is we combine these two into 1. We got the a out, so it would be a out of square root would be just a squared out is just a in front. We can take it front of the integral sign as well, it's just a constant. And what we'll have left is 2 times a 0 to pi 2 plus 2 cosine, so on. So this is the same as 2 times 1 plus cosine theta, and of course at that point. And there's a formula which can tell that 1 plus cosine theta is 2 cosine squared theta of 2. So we can put that there. And we get here another 2. We have 2 times 2, so that's 2 squared. So we can take one more 2 out of the square root. And again, in front of the integral sign, it's just a constant multiplier. Now we have cosine squared and a square root, so those cancel out each other. So what we get is from here 4a and cosine theta over 2 d theta. Integration limits are still the same, and then we get this. Technically, you could put some parentheses here, but it doesn't matter because the constant multiplier is just a constant multiplier. So sine 0 is 0, and sine pi over 2 is 1. So what we get is just 8a times 1, which is 8a. Okay, and that was that example. So after rotating parametric curve, this is slightly older lecture. I think we skipped this. So a cosine cube t, y equals a sine cube t. This is a symmetric curve called an asteroid. Astra is Latin for star, so it's a star-shaped curve. And it's symmetric, so we can take just half rotations out of it. But that's the same, so what the formula here means, this is how long is the circle segment, how far it is, so because we're counting together how many of these circle rotations there are. So, and one full rotation is 2 pi times the radius, and this here is the radius, and this here is the 2 pi. And ds means that how far we move sideways when we calculate one of those bands. So there we get the surface area. And this absolute value of y here is our g function. So it goes there. And then this ds unit is this Pythagorean theorem part here. So asteroid looks like that. And we only now need to consider this section, because once we rotate it, this, then and keep on rotating until there. So we're going that way. This one is going to be exactly the same. So we need only to rotate that part to get one full rotation. And this is just mirrored. So on the center line, whoops, we get just the same twice. So if this is 1 unit, then this is twice the same to get the part. Alright, so okay, let's do the derivatives. So to get the distance unit, we get cosine squared t sine t times minus 3a, and then we get 3a sine squared cosine t, sine squared t cosine t. And so the Jacobian looks awful at first, but we notice that there's a common term, 9a here, 9a here. So we can take that right out. Square root of 9a squared is 3a. And then we have at least 2 cosines and 2 sines. At least 2 sines, at least 2 cosines. So what we can take cosine squared t sine squared t. This is supposed to be on the square here. So out. And taking a square root of that is cosine t sine t. What we have left is cosine squared t plus sine squared t. And this here is 1. So square root of 1, all we have left is 3a cosine t sine t. So looked a bit scary, but not really. Surface area volume. So okay, we're having a sine wave from 0 to pi over 2. It behaves like this. It's greater than 0. So the absolute value is just itself. So this is this part which technically should have absolute value bars around it, but those have no meaning in this case, so we can drop them off. What we get here is 1a, a squared, and 3 times. Note this is the rotation, this is that we're taking symmetrically twice the same thing. So we get 4 pi's and 3a squared from here. So 4 times 3 is 12, and pi a squared. What we have left here is sine to the power 4 cosine t. That's not a nice thing to integrate. So we can make a substitution. U equals sine t. du is 10 cosine t dt. Ooh, we've got the cosine dtt right here. So all we have left is u to the power 4. Note that this is sine pi over 2 here, and this is sine 0 here. So we have also done limit swaps, and then the integral for u to the power 4 du is 1/5 u to the power 5. Well, technically plus c, but we're having a definite integral, so we do not need to have a plus c here, because we would have plus c minus c. So what we get here, substitute 1 here, 1/5, substitute 0, that's 0. So we get 1, so this part evaluates to 1/5, which is 12 pi a squared times 1/5. We get the end result. All right. Polar rotation is not actually part of the curriculum, but it would go similarly if we can solve y or x. So similar formula, but then we'll work probably this formula or the relevant x formula in polar coordinates. So replace this y equals as from trigonometry, or depending which way we rotate. And of course, one interesting thing here is that we could rotate the polar curve. See, volumes will be discussed in Engineering Mathematics 3, so this is why so that's 3 dimensions. We're going only to 2 dimensions on this course, so that's why we're not discussing really volume here. But you probably can already see the applications. Normalization, special case in parametrization, so we scale a phenomenon. Widely used in statistics, so for example, if we sort some data and we get that the data points are like sorted, and then this would be 1, and if we want to read that how much of the data is below that line, we check where it's the intersection and check maybe it is 0.5, so okay, there's an 0.5 chance that we're on this area. Also, this allows us to compare shapes, so maybe we have 2 phenomena. One is, okay, we have the shape here, and then another phenomena is we have the shape here. So when we scale them so that these go similarly, we can allow, for example, does these curve the same way. And then new concepts which we're gonna need to have the next example. So remember this parametrized curve, this RT, handwriting is xt times I plus yt times j, and the velocity is the derivative of that. So time derivative of place is velocity, and then here we are having, notice non-boldface one is the speed. So this is the tangent is the unit vector of velocity. Or in time, this should be s. So then we get just that. So if we have parameterized by distance traveled, then this is just the derivative here. But if we have parameterized by time or some other parameterization, then we need to consider the velocity. the boldface is the resultant vector, not radius, but of course if we take the distance of that, you'll get the radius. So the radius and the angle representation of a vector will end up us looking a lot like polar coordinates. And more new concepts, so the curvature. So okay, this is kind of a tangent vector squared is taking a dot product by itself. Those are unit vectors, so the dot product will be 1. And if we differentiate by TS, we haven't really talked that much about differentiated vectors, but you could do this unit-wise if necessary, and the end result will be that when we're differentiating t squared, we're getting this kind of a thing. And differential of 1 is 0. TS is the perpendicular, because the dot product between those two is 0, these must be perpendicular to each other. So this is a kind of a normal vector, but no hat yet, just a dash. So not a unit vector. And how long this is what we call the curvature, which we mark with a Greek letter kappa. And now when we get unit vector, so if we divide it by the curvature, we do so divide this normal vector with the curvature, we get the unit normal. And this 1 over curvature does also have a geometrical interpretation. So this rho is radius. So this P looking letter is one of the Greek R's. So rho of that. So this tells what's the radius. So if we're having a curvature like that, constant curvature, then this will be on a circle radius of rho. Where do we need that? For example, if we design any kind of a conveyor, road, track, maybe even some kind of piping and so on. So acceleration can be calculated like that. Note there's a velocity vector, not the speed vector. The speed vector, not the velocity vector. So there's a no boldface here. It's not a vector. It's a I told about it. This is a scalar. Scalar. Also, this is also a scalar. So curvature times this kind of goes back to, so this normal vector is a unit vector, and this curvature times normal vector actually goes back to the dt ds times velocity squared, and we do get the angular velocity here. And it's times speed squared, we get the angular velocity. We get the radial velocity, of course, or radial acceleration. Yeah, radial acceleration. So this would be the acceleration vector. Of course, if we're talking about circular motion, then we do get incredibly simple interpretation of this being rd theta, and the normal vector being, well, the kappa normal being dr. So yes, we're going here towards the acceleration formula, so change in velocity, or second derivative of location. And why we're talking about acceleration is, you might remember that F equals ma. So this tells what kind of forces will affect the vehicle or some part on a conveyor or so on. And one way is that we do bank the road such a way that when we're having, so this is one thing where you can use projection. So if you have a banked road with an angle, gravity is going to point down, but then the components of gravity when we put on the roadway is that way and that way. That component is how well we press towards the road, and this component is how the banking in the road does help counter these forces. So there's one more application of where we might want to divide into arbitrary components, or components in an arbitrary direction. And masses are going to cancel each other, so we're just going to need the curvature, indent speed, and do the projections. So because these are unit vectors, so when projecting it's just dot products, we can get so this is what we need to cancel out, this speed squared times curvature, and we get the acceleration sideways. And so acceleration is the normal direction here, and then F equals ma, we are kind of opposed by mg, and this tan and the component will be tan theta mg, and that should be this an, and times m. Okay, these cancel out. Divide by g, we get this an over g must be tan theta. So from this we can solve that theta equals arcus tangent an over g, and that's how you could solve what should be the angle of a road if we're getting at what velocity, if we're wanting to have a specific velocity and we're having a curvature in the road. Okay. And of course, this is, we can run the numbers backwards. So if we're allowed to have a certain degree of bank, then what curvatures are allowable for the road if we have a specific speed limit? And of course, we might have some limits of what amount of sideways acceleration we have. So usually tires or other parts that need to contact with the conveyor or road do have some traction, so we have some sideways acceleration. So for comfort, we probably don't want to pull that many G's on public roads. Or then we might consider what's the traction we can expect the cars to have, how the road is shaped. Then we could calculate what is the maximum allowable speed limit, probably with some slack also given for the safe operation and people who might be speeding anyway and so on. And yes, then also acceleration should behave smoothly, so we don't want to have sudden banks in the road. So gently increasing curvatures, these can also be calculated. And also we do have then many types of mechatronic controls. So and it turns out that there's also more efficient toolpaths where we have even up to the third derivative to be continuous. And this is it for our topics for today. Let's see, there we go.